Hello, and welcome to your AP Statistics Chapter 26 lesson on Chi-Sq goodness of fit. We're actually splitting Chapter 26 up into two parts. Today we're going to learn about Chi-Sq goodness of fit, and next time we will learn about Chi-Sq tests of homogeneity and independence. Goodness of fit. A test of whether the distribution of counts in one categorical variable matches the distribution predicted by a model is called a goodness of fit test because you're testing how well the prediction model fits what is actually seen. How well does what we expect according to the model fit what we observe in the actual data? As usual, there are assumptions and conditions to consider. The first is counted data condition. Check that the data are counts for the categories of categorical variables. The second condition is going to be the randomization condition so that we can make the independence assumption. So we're going to need to assume that the counts in the cells should be independent of each other. And one way we can check that is that the individuals who have been counted and whose counts are available for analysis should be a random sample from some population. The sample size assumption, we must have enough data for the methods to work. And so in order to make this assumption, we have to check the expected cell frequency condition. And we should expect to see at least 5 individuals in each cell. So this is dependent on the model and the total sample size. It's not dependent on what we observe. These are expected counts. And this is similar to the condition that NP and NQ be at least 10 when we tested proportions, but now it's 5 for each cell. Okay, so calculations. Since we want to examine how well the observed data reflect what would be expected, it's natural to look at the differences between the observed and expected count. And you see there the little abbreviation that's used a lot. OBS for observed and EXP for expected, and looking at the difference of observed minus expected. These differences are actually residuals, so we know that adding all of the differences will result in a sum of 0. That's not very helpful. We'll handle the residuals as we did in regression, by squaring them. To get an idea of the relative sizes of the differences, we will divide each squared difference by the expected count for that cell. The test statistic called the Chi-Sq or Chi-squared statistic is found by adding up the sum of the squares of the deviations between the observed and expected counts divided by the expected counts. So Chi-square, that's the symbol for Chi-square, equals the sum across all cells of the difference between observed and expected squared divided by expected. The Chi-Sq models are actually a family of distributions indexed by degrees of freedom, much like the t-distribution. The number of degrees of freedom for a goodness of fit test is n-1, where n is the number of categories. Now this gets confusing because usually we do n as sample size, so just remember this. In fact, I would write it down as categories minus 1 or cat minus 1 because it's the number of categories minus 1, not the sample size minus 1. And people get confused on that all the time. The Chi-Sq test statistic is used only for testing hypotheses, not for constructing confidence intervals. If the observed counts don't match the expected, the statistic will be large. It can't be too small. So the Chi-Sq test is always one-sided. If the calculated statistic value is large enough, we'll reject the null hypothesis. The mechanics may work like a one-sided test, but the interpretation of a Chi-Sq test is in some ways many-sided. There are many ways the null hypothesis could be wrong. There's no direction to the rejection of the null hypothesis. All we know is that it doesn't fit. Okay, so the first thing we do for the Chi-Sq calculation is find the expected values. Every model gives a hypothesized proportion for each cell. The expected value is the product of the total number of observations times this proportion. And then you want to compute the residuals. Once you have expected values for each cell, find the residuals, the observed minus expected, and then square the residuals. Now you want to compute the components. which are the squares of the residuals divided by the expected number for each cell, and then find the sum of the components, and that is the chi-square statistic. Find the degrees of freedom. It's equal to, it has here the number of cells minus 1. That's going to be your number of categories minus 1. And then you're going to test your hypothesis. Use your chi-square statistic to find the p-value. Remember, you'll always have a one-sided test. Large chi-square values means lots of deviation from the hypothesized model, so they give small p-values. Goodness of fit tests are likely to be performed by people who have a theory of what proportions should be and who believe their theory is to be true. Unfortunately, the only null hypothesis available for a goodness of fit test is that the theory is true. As we know, the hypothesis testing procedure allows us only to reject or fail to reject the null. We can never confirm that a theory is in fact true. At best, we can point out only that the data are consistent with the proposed theory. Remember, it's the idea of not guilty versus innocent. After getting trounced by your little brother in a children's game, you suspect the die he gave you to roll may be unfair. To check, you roll it 60 times, recording the number of times each face appears. Do these results cast doubt on the die's fairness? Okay, so here we've got the face of each face of the die, 1, 2, 3, 4, 5, and 6. Those are the possible outcomes. And here's the count out of 60 rolls. If the die is fair, how many times would you expect each face to show? Well, you'd expect each one to be equally likely. So the probability for each face would be 1/6 for each roll. So 1/6 times 60 is 10. So 10. What kind of distribution would the outcomes follow if the die is fair? Since all 6 faces would have the same expected number of outcomes, 10, the distribution would be uniform. Okay, remember that's what we call it when you expect the same number of observations for every outcome. State your hypotheses. All right, my null hypothesis is the die is fair, or a uniform distribution is a good fit for the outcomes of all rolls of this die. Versus our alternative, the die is unfair, or a uniform distribution is not a good fit for the outcomes of all rolls of this die. We're going to check the conditions. Okay, first thing we want to check is that there's counted data. Well, the data are counts of outcomes for the roll of a die. We want to check randomization so that we can make it the independence assumption. The outcomes of the roll of a die are random. Okay, so that indicates that they're independent. Expected counts so that we can assume that our sample size is large enough. The expected count for each face is 10, which makes them all greater than 5. So we're good to go. How many degrees of freedom are there? It's the number of categories minus 1. So 6 minus 1 is 5. Notice again, it's the number of categories minus 1, not the number of rolls minus 1. Okay, so that's very important for you to know. We're going to find chi-squared and the p-value. Okay, so we want to do this in our calculator. So you're going to open a new document in a spreadsheet. So you're going to do a spreadsheet page, make an observed list and an expected list. In the observed list, put the counts for each face. In the expected list, put the expected number 10 for each face. And you can name them observed and expected, or you can name them whatever you want to. Then you're going to select Menu, Statistics, Stat Test, Chi-Sq GOF. Select Observed for the observed list and Expected for the expected list, and enter the degrees of freedom 5 for DG and select OK. So chi-squared is 5.6 with 5 degrees of freedom. Notice I reported my degrees of freedom. You want to do that. The p-value is 0.3471. So we're going to state our conclusion. Well, let's interpret our p-value. If the die is fair, that's our null hypothesis, okay, that the die is fair, the distribution is uniform, we would get results at least as extreme as the ones we observed 35% of the time, approximately. Well, that's not very surprising, okay? So Due to our large p-value 0.35, we fail to reject our null hypothesis. There is no significant evidence that the die is unfair. Or another way to state this is there is no significant evidence that the distribution of die faces is not uniform. The data are consistent with uniformity in the distribution of die faces. Let's look at another example. We're going to look at exercise 8 from page 643. In its study, When Men Murder Women, the Violence Policy Center reported that 1,857 women were murdered by men in 2005. Of these victims, a weapon could be identified for 1,752 of them. Of those for whom a weapon could be identified, 966 were killed by guns, 390 were by knives or other cutting instruments, 136 by other weapons, and 260 by personal attack, batteries, strangulation, etc. The FBI's Uniform Crime Report says that among all murders nationwide, the weapon use rates were as follows: guns 63.4%, knives 13.1%, other weapons 16.8%, and personal attack 6.7%. Is there evidence that violence against women involves different weapons than murders in general in the United States? Okay, so our null hypothesis would be murders among women have the same distribution of weapons as all murders in the United States. There's no difference in the distribution, no significant difference. The alternative hypothesis is murders among women have a different distribution of weapons as all murders in the United States. So the null is that the model fits. The alternative is that the model doesn't fit. Just like with the die. The null is that the model of uniformity fits. The die is fair. The alternative was that the model didn't fit, that the die was unfair. Okay, so let's check our conditions. The data are counts of murders. Each murder is plausibly independent of others. The expected counts are all at least 5. Okay, and you do this by taking the percent as a decimal and multiplying by the total number of women. Now you have to be careful here because you only include the women for whom the murder weapon could be identified. So our sample size was actually 1,752. So you do 0.634 times 1,752 and you get 1,110.7 women were expected to be killed by guns, and you keep going. So knives and other blades would be 0.131 times 1,752, which is 229.512. And then just personal attacks, you would expect that 6.7% of the 1,752. So that would be 117.384. It looks like my other weapons got moved down here. Let's go ahead and move it back up where it belongs. I don't know how on earth that happened. Just right here. There we go. Sorry about that. And because all 3 conditions are met there, we've got counts, we've got plausible independence, and we've got expected counts at least 5, we can carry out our test. So I will conduct a Chi-Sq goodness of fit test. Look at the last example for CAS instructions. In fact, I encourage you to do that. To stop now, go back and look at the last example, get the instructions, and make sure that you end up with the same Chi-Sq test statistic and the same p-value. So we get a Chi-Sq test statistic of 389.54. We have 3 degrees of freedom because we have 4 categories, so 4 minus 1 is 3. And then our p-value is approximately 0. So we're very surprised. So due to our small p-value, 0, we reject the null hypothesis. We have surprising counts given the model that we were given. There is significant evidence that murders among women have a different distribution of weapons as all murders in the U.S. So we say there's significant evidence, and then we just kind of restate our alternative. All right, next class time, you will finish up Chapter 26, and we'll talk about chi-square tests of homogeneity and independence. But this is all for today. We just wanted to focus on goodness of fit. I will see you next time. Bye.